Welcome to the deep dive. Today we're jumping straight into the geometry from your sources, shapes with straight lines.
That's right. We're looking at what makes these figures work based on the material provided.
Our mission really is just to unpack what the sources say about them, from basics to, well, some surprising bits.
Exactly. So the sources kick off with rectilinear figures. It's just a term for shapes made only of straight lines.
Okay.
And the main type we're talking about are polygons. Simple idea, closed shapes, flat plane, at least 3 straight sides.
Right, and the names follow the sides, like the sources lay out. Triangle for 3, quadrilateral 4, pentagon, hexagon. It keeps going.
Yep, that's the system.
The sources also quickly mention convex versus concave. Convex is sort of all angles pointing outwards, less than 180.
Exactly. And concave means there's at least one angle kind of pushing in,
Yeah.
more than 180 degrees, like a dent.
Like a bite taken out, yeah. But generally, the focus is on convex ones, right? That's what we usually mean by polygon.
That's usually the assumption, yeah. Unless stated otherwise.
Okay, so what key properties do the sources highlight? Angles seem big.
Angles are definitely central. The first big rule mentioned is how to find the sum of all the inside angles of any polygon.
Ah, the formula.
Yeah, it's given as 2 and 4 right angles, or maybe easier, n2 times 180 degrees. Din is just the number of sides.
Okay, let's check that. Triangle and 3, so 3 to 2. 180 degrees, yep.
Right.
Quadrilateral and 4, 4 to 2, 180, 360 degrees. Okay, it works. Makes sense. It depends on the number of sides.
It does. But here's something the sources point out that's really quite cool, maybe a bit unexpected.
Oh.
The sum of the exterior angles. If you walk around the shape and add up all the turns you make at the corners,
Yeah.
that total turn, the sum of those exterior angles, it's always 360 degrees for any polygon. Doesn't matter how many sides.
Always 360 for a triangle or a 20-sided shape.
Always. 360 degrees. One full turn. That's a constant the sources really emphasize.
Wow, okay. That is interesting. And that probably makes things easier for specific types of polygons, like regular ones.
Absolutely. It simplifies regular polygons massively.
Yeah.
Your sources define those as having all sides equal and all angles equal. Perfect shapes, basically.
Like an equilateral triangle or a square.
Exactly. And because we know the total exterior angle sum is fixed at 360.
Ah, so for a regular polygon with insides, each exterior angle must just be 360 divided by n. Simple division.
Precisely. And since the interior and exterior angles at any corner add up to 180 degrees.
You just subtract the exterior angle from 180 to get the interior one? Okay, that 360 rule is pretty powerful for regular shapes.
It connects everything nicely. So building on that, the sources dive deeper into quadrilaterals, the 4-sided ones.
Great, we know their inside angles add up to 360 already.
We do. But the interesting stuff the sources cover is how different rules about their sides and angles create, well, families of quadrilaterals, each with its own special features.
Okay, let's walk through those families from the material. What's the starting point?
The trapezium. Its defining feature, according to the sources, is just one pair of opposite sides being parallel. Only one.
And there's a special type mentioned.
Yeah, the isosceles trapezium. That's where the 2 non-parallel sides are equal length. And interestingly, the sources note this causes the base angles to be equal, and also the diagonals end up being equal length.
Okay, so one pair parallel. What if both pairs are parallel?
Then you get a parallelogram. Both pairs of opposite sides are parallel. And the sources stress that this parallelism leads to other automatic properties.
Yes.
Opposite sides become equal length. Opposite angles become equal. Any 2 angles next to each other add up to 180 degrees. And crucially, the diagonals cut each other exactly in half. They bisect each other.
That bisection thing seems important.
It's a key consequence of the parallel sides, yeah.
And then we get special parallelograms, right? Like the rectangle.
Right. A rectangle is a parallelogram, but with the added condition that all its angles are right angles, 90 degrees. It gets all the parallelogram properties, but the sources highlight a specific result of the right angles. The diagonals aren't just bisecting, they're now also equal in length.
Okay, equal diagonals for rectangles, then there's the rhombus.
Also a parallelogram. But its defining feature is that all 4 sides are equal length. Again, it inherits parallelogram traits, but the equal sides add new diagonal tricks.
Oh, like what?
The diagonals still bisect each other, but now they cross at a perfect 90-degree angle, and they also cut the corner angles, the vertex angles, exactly in half.
Right angles and bisecting the corners. Okay. And the last one, the square. It seems to have everything.
It pretty much does. The sources position it as the combination of a rectangle and a rhombus. It's a parallelogram, is a rectangle, and is a rhombus.
So all sides equal, all angles 90 degrees.
Correct. which means its diagonals do everything. They're equal length, like a rectangles. They bisect each other at 90 degrees, like rhombuses, and they bisect the vertex angles, also like rhombuses. It's the peak quadrilateral, in a way.
Got it. So summarizing this deep dive from the sources, we've looked at the basic rules for straight-sided shapes, polygons, this really neat constant sum for exterior angles,
The 360.
and then how adding specific rules for sides and angles in quadrilaterals gives us these distinct families: trapezium, parallelogram, rectangle, rhombus, square, each with unique diagonal behaviors.
Exactly. It builds up logically based on those defining properties.
Which leaves us with a final thought from this exploration. How often do these rules, that constant exterior angle sum, or the way diagonals work in a square, actually show up? In buildings, design, everyday objects.
Yeah, something to maybe keep an eye out for.
Yeah.
Where do you see this geometry, these straight line rules playing out in the world around you? It's often hidden in plain sight.